Hello and welcome. Today we'll be talking about some testing that we've recently completed for a local government client of ours in the New South Wales, Sydney metropolitan area. We were doing some testing with them to understand how some of their systems would accommodate lower temperatures for heat pump installation and what the flow-on effects may be in their buildings were we to reduce the temperatures and potentially even the capacities of their existing system. So this particular council has ambitious targets to reduce fossil-based Scope 1 emissions, obviously the burning of natural gas on site for heating hot water being the main source of these for this particular council. And due to legacy conditions, the electrification of several large boilers for this site was challenging. There are electrical capacity concerns. There are also significant spatial constraints, and the site has 80-degree heating hot water set points. What this meant is reducing the heating hot water temperatures and considering a total capacity reduction, if possible, does provide a quite logical path to minimizing heat pump requirements. When we looked at the possibility of doing some desktop approach to completing this assessment, but due to the organic growth that this site's experienced over a number of years, it's not really viable to consider a desktop approach, and you have to do some on-site testing to see where the strengths and weaknesses of the site really do lie. So during the winter months of 2024, we worked with them and at one of their largest sites to complete some testing and assess the high-level viability of this approach. In terms of outcomes, to take you straight to the point, in two testing increments, we lowered the heating hot water from 76, where it was the start point, to 65. So it went 76, 70, 65. There were no discernible impacts to space temperatures during testing, and that is based on the testing conditions during the lower temperatures and versus the baseline that was before. What we did find, though, is some poorly performing areas that were identified. The lower temperatures of the heating hot water actually didn't exacerbate these. It was really just a reiteration of the spaces that were already recognized as a concern. There is no increase in there was no increase in stakeholder complaints experienced during the testing, and the testing was done during some particularly cold days in Sydney. And we did find a number of issues that weren't expected and required further investigation. Some we were able to tweak during the testing, but others will require a little bit more work and do give us the basis to, I guess, follow up initially where some of the weak points in the system might be. As an example, there are some zone set points at 25 degrees. So it's not... I guess it's not a surprise that those temperatures those zones failed to reach that point during those cold days. So once the 65-degree temperature was reached, unfortunately, some warm weather came through and we couldn't continue the testing. I'll explain with some data as to why that was a particular problem for this site. But to the planned testing for this year, 2025, will aim to continue those increments down, ideally down to 55 degrees, for ideal heat pump configurations. So the testing approach, we established the data logging, and that was with a 15-minute minimum interval within the BMS. We looked at all zone temperatures and we monitored all heating hot water valve positions, heating hot water flow and return temperatures, and pump operation. And believe it or not, this was actually the hardest part. It took quite some time to get the right people in the room and coordinated simply to establish this data logging. So the BMS was there and it had the points, but I guess the cautionary tale here is please don't underestimate the data that isn't currently logged and the amount of time it will take to coordinate getting that system in place. We then lowered the temperature from 76 to 70, and we actively monitored that for a period of at least 1 week. We looked at the zone temperatures, particularly on warm up, and you'll see why with some data shortly. We looked at boiler flow and return temperature profiles. We looked at any alerts, system alarms, and complaints that were related to temperature in the space. And we also reviewed the operation of poorly performing zones. Again, I'll show you what I mean with some data in the coming slides. The next point speaks to the next step, which was when we saw that there were no conditions that were of concern. After 1 week at 70 degrees, we reduced the temperature to 65 and then repeated the activity. So you can see how the temperatures behaved. This is the flow and return temperatures for the heating hot water set point. You can see the set point reducing from 76 to 70 and then down again to 65. We rarely witnessed, any concerns in terms of the temperature delta. So the design temperature delta is 20 degrees. Obviously, heat pumps generally don't like to accommodate 20 degrees, and it requires a lot more reconfiguration of your primary secondary loops in the event that you need to maintain this. So temperature delta was averaged at about 5 to 8 degrees. And the one point I'll also make is this was a fixed flow hot water system. So there's further opportunities to, rationalize energy use and system performance with the introduction of variable flow systems that could be implemented as part of any heat pump upgrade. We looked at the boiler energy production, assuming about a 90% energy efficiency. The rated boiler output was 292 kilowatts. And you can see the heating hot water outputs for the testing period. So I guess what that tells us is with some additional tuning and potentially some hot water storage, just to trim out those really sort of peak points, it would suggest that a 40-degree reduction in peak capacity would be achievable. So that's 40% less in terms of your electrical requirements, structural, spatial, etc., in terms of the heat pump that you would ultimately be installing. And when we look at the real, crux of the problem, which is your zone temperatures, we see quite a big spread across the site. Now, the purpose of putting this slide up is really just to point out why it's critical that you do this testing during cold periods. So you'll see during the initial week of testing where it was 70 degrees, we had quite a large spread, and you'll see the ambient temperatures below were quite colder. That tightened up quite a bit when we moved into the next week at a lower temperature because the ambient temperatures were quite a bit higher in that week. So it is important to get this testing done during the coldest parts of the year. You'll also see one rogue zone that we found, and we were able to implement some changes to that zone during the first week of testing, and you'll see that it pulled its way into line towards the back end of that week. So not all poor outcomes reflect the reduced temperature as the cause. That particular outcome was not related to the temperature at all, and we were able to rectify that quite quickly. When we start to look a bit more finely at the details of the zones, what I've done here is I've overlaid, I guess, an occupancy window and requirements. So between office hours, 8:30 till 6, and a temperature requirement of 21 degrees. You can quite easily see here where your zones are not achieving temperature. Now, it might be that they're not achieving temperature just for a small point in the morning warm-up, or as you can see, for some of them, they weren't achieving the temperature requirements all day. So that tells us that there are a few areas where targeted intervention may be required. You may need to look at those spaces particularly and have a look. Maybe they do need an increase in the coil sizes. Maybe they need some additional insulation. What we found was there's quite a bit of building fabric and insulative areas that could be improved that would likely impact that performance. But the good thing here is you can see that there's a lot of zone temperature profiles that far exceeded the requirements, which indicates that for the vast majority of the site, only small tuning would be necessary to have everything fit within that comfort and time profile. This is to look at the valve position. So obviously, achieving the zone temperature set point is critical, but actually understanding how the valves are behaving during the day gives us a little bit more of an understanding as to how the system is performing. So we've got here a few good zones and a few bad zones, just as an example. And again, this reflects that it's unlikely that you'll need to replace all of the coils to achieve the lower temperatures. But you may need to work on some, or even in particularly cold situations, you may need to consider a hybrid or a boost option, where perhaps you've got a little bit of natural gas there just to boost the temperatures during those really cold times. So the bad position, the bad zones, you can see the valve opens 100% for warm up. The temps, they rise very, very, very slowly, but the valve stays open 100% throughout the day. So having this data logged will tell you immediately where you need to go to look for the zones that are problematic at your site. Communications and contingencies are really important during this testing because we actually don't know how some of this testing may impact the site. So we needed to have all outcomes covered and planned for. So we had a number of people involved, and we were in direct communications with during the planning and the testing. As an example here, we had the facilities executive who approved the plans, and we informed them daily on how we went. Sustainability, they were more about the coordination and assistance of the facilities guys. The FM manager, they coordinated on-site works and they were in charge of the tests. And asset management, we had discussions with them for capital plan alignment. And of course, we had our controls technician. They were a third party. They enabled some of the testing and the interrogation of the outcomes, and they were, of course, on call in the event that we needed any changes or adjustments made during the tests. We didn't make much we didn't communicate much with the field stakeholders, and the purpose for this was that if you tell someone you're going to reduce the temperature of their heating, there's almost a guarantee that they will feel colder. We believe that we had enough in place in terms of contingencies and management information as to the performance of the testing, that we would catch any conditions before they became too concerning for the stakeholders. And they were informed of building tuning activities, and we did include in our communication a refresher as to how you would go about informing facilities management of any concerns during the period. We also had some contingency rollbacks in place. So the rollback is basically just to go and increase the boiler set point. The abort call would be based on complaints and sensitivities of the area. And importantly, we had the site FM with the appropriate authority to issue those abort calls. We didn't have to go through management, which could delay that and result in a situation that was more difficult to control. But there were some limitations we had to work through. The site attendance where the boiler was located was not every day. However, the boiler set point was not controllable on the BMS, so we needed to have someone on site in the event that we needed to bump it up. So we had to have people sitting in close proximity so that we could enact those contingency plans in the event anything went too far out of control. And I guess some of the other limitations are the controls understanding. Similar to many sites, most of the controls and the specifics about the controls is understood by outsourced third-party contractors. This lack of understanding and reliance on others, it did result in quite a bit of unknown during the planning of the testing and the analysis of the outcomes of the testing. But this can be worked through with the appropriate skill set on the testing team. So, in terms of things that may have been unexpected during this testing and things that we discovered as part of the project, uh, I guess nothing that was too controversial. However, there were a number of discoveries that even the facilities management on site didn't know existed and could make some immediate improvements to the site in terms of improving the conditions, the performance of the system, and the energy efficiency. Once those improvements are made, that obviously will assist in the improvement to the heat pump specification that can be achieved. So, as an example, we found some zones that did not achieve set points, and when we analysed those particular zones, it was evident that, well, yes, those zones have some building fabric issues that are known and are planned to be treated at some point in the near future, which is great. They're the sorts of things that you actually need to understand before you install a heat pump, so that you don't oversize the capacity. Another point was zone temperatures that were quite high in terms of set points. So there were some zone set points that were 25 degrees, which is very high, especially in New South Wales context. And the reason for all of that appeared to be just a simple controls adjustment at some point in the past, likely to address a hot and cold or cold complaint that never actually got properly addressed. So, things like the location of the sensor within the room, open windows, heating and cooling that are influencing one another in different zones. All of those things were discovered and able to be treated quite simply and in a way that addresses a number of issues right now and adds to the heat pump business case when they go ahead. That's all I had to you about today, and thank you very much for watching. My name is Michael Snow, and I hope you enjoyed what we just ran you through. Thanks. Bye.